We are discussing one-dimensional unconstrained optimization, and in our last lecture we have talked about random search. Random search is an easy technique where we randomly generate certain points and try to see if that point is indeed the optimum. Now we'll make our search slightly more systematic, and in this lecture we'll look at golden section search. In golden section search, we start by identifying an interval within which the optimum resides, and then we define an iterative scheme through which we'll continue to shorten the interval around that optimum. So let us see how we can perform this. The golden section search comes under the bigger umbrella of what we call as the region elimination methods. The goal here is to find the optimum within a specified interval, and for our discussion we are only taking that kind of intervals where in that interval there will be one and only one stationary points, only one a prime x equals 0 point, and this kind of function we will call them unimodal function. So let us take up a function y equals fx here, and you can see in this figure that it has one and only one maximum around this point. The function we are interested has this bound of x1, x2. Now our goal is to iteratively reduce this x2 minus x1, or bringing this x1 and x2 close to each other iteratively. So we start by taking two new points, x3 and x4, in a way that x3 and x4 will be within this x1 and x2 interval, and x3 is less than x4, which means x1, then x3, then x4, then x2. This is how we will arrange them. Now after we select this, what we do is that we evaluate the value of the function as x3 and at x4. Once we evaluate these functions, we compare them. One of two cases can happen: x3 is less than x4 or fx3 is less than fx4. You can say that they could be equal, but in real number calculation they are never really equal as such, so either less or greater. But even if they are equal, we can handle that, so we'll come to that. But this is the general case: either fx3 is less than fx4 or fx3 is greater than fx4. So what happens? Let us take one of them. Let us take this fx3 is less than fx4. Then what? So this point is less than this point. Now you think about it, we are looking for the maximum here. Maximum can be in this interval between x3 and x4, and between x4 and x2. One of these three intervals maximum can be there. Now the additional condition we have given that fx3 is less than fx4. When fx3 is less than fx4, but the maximum is over here between this x1 and x3, then the function goes like this. This is the maximum, so it should go above this fx3 point, and then it comes down. As it comes down, because fx4 is greater than fx3, it should again go up. But it cannot go up, because if it does go up, if the function is like this, then there will be two stationary points. One is here, one is here, which tells us that we cannot have the maximum between x1 and x3. But can we have the maximum between x3 and x4? Yes, of course, we are having the maximum between x3 and x4. We can see that. Can we have the maximum between x2 and x4? Well, if it does happen, then the function will go like this, and then it will come down like this, and that is perfectly alright, because fx3 is less than fx4. So it is perfectly alright to have a function like this. So therefore, the maximum can be in this interval, but not in this interval between x1 and x3. So what we can do, we can discard this x1 point and we can replace it with x3, because maximum can be within x3 and x4, and also it can be within x4 and x2. We can clearly say that maximum will be within x3 and x2. So what we can do, this interval x1, x2, we can replace that with x3, x2. Now if the reverse happens, then of course the reverse will happen here. So you can simply reverse this picture and visualize what will happen. I'm leaving this for your thought experiment. It will be x1, x2 will be then replaced by x1, x4. So in one case this is x3, x2, in another case x1, x4. Either way, you see that we have shortened the interval. In the limiting case, if fx3, fx4 are equal, then of course this x1, x2 will be replaced by x through x4. That is actually very good, but then that is unlikely to happen because in real number calculation, nothing is actually equal to another in real number. Now we can see that if we have this x3, x4 points, how we can reduce the interval methodically. But the question now comes that how we are going to get this point x3, x4 in a systematic manner. This algorithm we have just discussed, this is the general algorithm region elimination methods. And based on that, there are many different ideas. Every idea comes with a different strategy to find x3 and x4. Whatever x3 and x4 you decide, it will actually solution will converge. But the point is that we want to do it in less number of iteration. That's the real goal here. How can we do so? And there is no clear-cut answer on this. Golden search gives us one idea and we go with that in this lecture. But there are also other ideas. These are completely heuristic. Every idea it comes, it is believed that that's a better way than others. But it is very difficult to prove that one of these ideas will work for all kinds of problems. Let us look at the opposite type of function here where we have minimum in x1, x2. And we follow the same rule here again. Here we take this x3, x4 in between x1 and x2. And then we can have once again two different conditions. fx3 is less than fx4 and fx3 is greater than fx4. If fx3 is less than fx4, then this x2 and x4 we will interchange between them. So x4 will be my new fx2. And similarly, if fx3 is greater than fx4, this x3 will be my new fx1. It is exactly the same procedure. You can spend some time and do some thought experiment here that why it will happen. But the idea remains same, where, for example, your fx4 is less than fx3 in this case. And you can take a look that where the minimum can reside in this interval between x3, x4, in this interval between x1, x3, and in this interval between x4, x2. So because the minimum is here and x4 is smaller than x3, so what happens here? Can the minimum be here? No, it cannot be here. So let us see why it cannot be here. Let us say the minimum is over here. Then the function looks like this. And then we know that x4 is again less than x3. So it has to again come down. We cannot allow that. Then we will have two stationary points here. So this is not possible. Therefore, the minimum can be here, the minimum can be here, but not in this interval. So this x1, x2 is replaced by x3, x2. So x1 I have discarded, and we believe that the minimum will remain between x3 and x2. So this is how you can actually convince yourself for all four cases like this. Goal then remain the same, that this x3, x4, we have to find it in a way that we can converge the solution efficiently. And as I said that there are many methods. So we'll take up one, that is the golden search. So in this golden section search, what we do is that we select this x3, x4 using a particular rule. What is that rule? First rule is that we take up that the new interval will be constant multiplied by the previous interval. So if my old interval is L, that is x2 minus x1, my new interval could be x2 minus x3, because one of them, in one iteration, one of them will be changed. So my new interval could be x2 minus x3 or x4 minus x1. And I wish that for a constant c, my new interval will be the c multiplied by L. Now this is a good idea actually, because we now know in every interval how much there will be reduction in interval. So this goal now is to find out a good value for c. For that, we come to the second rule of golden section. Second rule of golden section is that it says that the same rule we apply to find x3 and x4. What does that mean? It says that let us start from this x1 and x2 point first, and then we try to find out x4. And I find out x4. So x4 minus x1 divided by x2 minus x1, this ratio I take, this gives us roughly that compared to the total length, how far this x4 is from x1. And then once I find the x4, now I come to this point x2, and now I focus on x2, x4 and x3. They should be related like a similar rule of x4 minus x1, x2 minus x1 ratio. So in this case, x4 minus x2 divided by x3 minus x2. These two ratio, we make them same. Now this rule for finding x3, x4, there is no bulletproof reason to take this rule and not something else. This is totally heuristic, and we found that this rule gives a good rate of convergence. Now what we do here is that if you look at x4 minus x1, that is C multiplied by L, x2 minus x1 is L. On the other hand, x4 minus x2, we change it like x4 minus x1 plus x1 minus x2. x3 minus x2 will be negative CL. Here, x4 minus x1 is CL and x2 minus x1 is L, so this is negative L. So now I have CL by L is CL minus L divided by negative CL. L cancels, so I can write C here 1 minus C by C. So it gives me an equation of C. I can really solve this equation and get a suitable value for C. If I solve it, it's a quadratic equation. It gives me two roots, but one root is negative. Clearly, we are not going to take a negative root here. So we take the positive root, and this positive root turns out to be 0.618. And this 618 is something, it's a historically very important number. It is used in architectural planning as well as in many natural phenomena. This is known as golden ratio, and that golden ratio mathematically comes from this idea that we have just discussed. We continue this process. In every iteration, the interval will reduce to 61% of the previous iteration, and this is how continuously the interval will reduce. At the end, this interval will be small enough so that we can say that yes, we have reached convergence. So let us now see our old problem here, that we were maximizing this function, that is our fuel economy, y equals f of x, ax cube plus bx square plus cx plus d, and abcd were given to us. This function comes from a regression, and we are interested to find out the maximum value of y. Here we have calculated the golden ratio. You can calculate it like that, or we can simply write this is 0.618. That's good enough. And this is a stopping criteria epsilon. This is our function. We want to maximize it. And our interval goes from 10 to 100. The x2 minus x1 is something that is necessary for us. That is the range L that we want to reduce. So we start from this x2 minus x1. Now I start a while loop. As long as this L is greater than epsilon, it will go. And our epsilon is 10 raised to minus 8. So very small epsilon. Once the interval comes within 10 raised to minus 8, you can say that we have basically hit the maximum in this case. So what we do is that we first find this x3 and x4 here. So this is where I am finding this x3 and x4 points. And once I have this x3, x4 points, I find this f of x3 and f of x4. Now I compare f of x3 and f of x4. If they are less, then x1 is taking this x3 values. Otherwise, this x2 is taking this x4 values. And then I calculate the new L, that is my x2 minus x1. Now I have a new x1, new x2, probably either one of them is new. So once the solution is converged, I can calculate this f star, that is the y value. Here x1 and x2 are basically equal. Their difference is 10 raised to minus 8. So wherever you calculate this f value of that, it could be fx2 as well, because x1 and x2 are 10 raised to minus 8 apart. So it doesn't really matter. So that is the value of this function, maximum value of this function. If you run this code, what you will get is 18.58, the answer. And that is exactly the answer we were looking for. This is 18.58 here. This is the answer we have got from analytical solution as well as from random search. Here, of course, you will see, if you look at this within this while loop, you will see that same calculation we are actually repeating again and again. So some of the calculations are actually duplicated, so you can remove them and make this program more efficient. Now we come to the other kind of problem where we minimize this function x square minus 2 whole square. It's a very similar looking problem. I have a different function here and I have a different interval, of course, between 0 to 2. But the logic goes very similar, except the fact that now this is a minimization problem. So when f3 is equal to x4, then x2 is replaced by x4 and otherwise x1 is replaced by x3. I continue in same way. At the end I have x star and fx star is f of x1. In this case you understand that this will be same as f of x2 almost, because the interval is 10 raised to minus 8, so they are very close to each other. If you run this program, it will give you the value of 1.414 for this x1 and this f star is 1.5 10 raised to minus 16. So it's very small number it has given. So we are good to go here. We can accept that this is the value indeed for root 2. It is actually, you can see that it is more accurate than what we have got from random search technique. So now we are ready to summarize our lecture. In golden search, our goal is to iteratively reduce the interval and we focus only on unimodal function. That means within the interval we have only one stationary point. And we can see that here the ratio C is constant, 0.618. Because this is constant, we can actually calculate initially, given the initial interval x2 minus x1, we can calculate initially that how many iterations will be needed to achieve the desired accuracy. This is a very good idea for any computer program if you previously know the number of iterations necessary. For your exercise, you minimize this fx equals x square plus 54 by x. You use golden search algorithm and also you solve this analytically and try to match both the solutions with each other. Thank you. That's all for this lecture. I'll see you in next class.